All right, so we just talked about chapter 7.6, which deals with potential energy. 7.7 has to do with conservative forces. And then 7.8 relates the two. So we're going to talk about conservative forces, and then we're going to talk about how that's related to potential energy. So a conservative force is one that is path independent. And what that means, maybe I phrased that poorly. Maybe I should say the work done by a conservative force is path independent. Right, so if we were to consider moving an object from point A to point B, no matter how we get there, the work done by a conservative force is the same. All right, so this has a couple of effects. First of all, if we look at any closed path, so that means if I go back to the point where I started, then the work by a conservative force on a closed path is zero, right? Because you end up back where you started. And you can think about this in other ways too. If we look back at our point A to point B, you can consider moving along path 1 from A to B and moving along path 2 from A to B. And now we could think, well, what if I move along path 1 and then I move backwards along path 2? So moving backwards along path 2 would do negative the work that we did along path 2. And that's equal to the work on 1. So it would add to 0 if I add negative that value, right? So just another way to think about a closed path here. And this is useful when you start looking at work cycles for steam operations and things like that. All right. So one key thing is the closed path. The other key thing is that means that it's only dependent on position, right? So the energy change is only a function of position. And that's key because that means we can make a potential. We can choose a reference and describe a potential energy. So it turns out that in order to have a potential, it needs to be a conservative forces. So that's our connection that we wanted to talk about, is potential energies are related to the work done by conservative forces. Right, and we talked about how we derive the work done on a spring and by gravity, right? If I take an object from the ground and I lift it some height h, what's the work done by gravity? All right, well, the force of gravity is down. And my delta x is up, so it's doing negative work. What is the value of that work? Well, it's the force times the delta x times cosine theta, which cosine theta in this case is -1 because it's 180 degrees out. And delta x is h, so we have minus mgh is the work done by gravity lifting an object a distance h. All right, if you'll recall from when we were talking about potential energy, we said that potential energy was mgh, and that's not a coincidence. The change in potential energy is equal to minus the work done by a conservative force. This fits in nicely with our work kinetic energy theorem because we can now take our net work equal to the change in kinetic energy, and we can break that up into work by conservative forces plus the work by non-conservative forces. And now if we replace our work by conservative forces with a potential energy, we can rewrite it this way to say that the work by non-conservative forces is the change in kinetic energy plus the change in potential energy, the total mechanical energy of the system. All right. So now you look at the special case. So in the special case that the work done by non-conservative is 0, we get that the change in kinetic energy plus the change in potential energy is 0. And that means that the total mechanical energy is conserved. It's where that word conservative comes from, is that we're conserving the internal energy here. And that means if we look at this equation, if the kinetic energy goes down, the potential energy has to go up. If the potential energy goes down, the kinetic energy has to go up. But the total energy is a constant. And the energy is exchanged between forms. All right, anything I want to say further with this? I think this covers it for 7.7 and 7.8. So we'll stop there.